Estamos para empezar. Buenos días a todos. Muchas gracias por su presencia. Ella es Ariana Valencia. Vienes desde la costa oeste a introducirnos en lo que es esta nueva adquisición del instituto para facilidad y apertura a toda la UNC de este equipo nuevo, es un escáner histológico de alta tecnología que va a presentar a Ariana sus facilidades. Así que bueno, acá queda presentada para que escuchemos su exposición y después pueden hacerle preguntas.
Hola, bienvenidos. Mi nombre es Ariana Valencia. Y yo soy el Field Application Scientist de Acoya en the Southwest. Yo soy de California. So today we're going to be
Para abajo la flechita para abajo. Ahí anda.
honestly. Okay. Okay, so today we're going to be talking about, we're going to have a fusion overview, and then we're going to go into multispectral imaging, and next we'll go into multiplexing with opal overview. So first we'll start with the fusion overview. We'll break up into parts, so if you have questions, you can leave them to the end or in between each section. Okay, starting with the Phenoimager platform. So it has unprecedented speed. It allows us to rapidly and accurately image whole slide scans using multispectral technology. To begin with, the Fusion has a standard throughput. Each run supports 4 whole slide scans, allowing us to process anywhere between a dozen to 100 slides a day. It's also very flexible because it allows us to acquire both bright field and fluorescence images. It is fully integrated with our opal assays and analysis software for unmixing, phenotyping, and spatial analysis. And finally, a unique feature of this instrument is it's a tunable workflow. So we have a second part of this instrument, which is called the PhenoCycler. Should you wish to upscale your discovery study, and that can be up to 100 plus biomarkers in use. Okay. The Phenoimager solution is a complete end-to-end solution with 3 major components. First, we start with our optimized antibodies and opal staining reagents. Second, we have 2 instruments. So the instrument you have here is going to be on the left-hand side, or we have our Phenoimager HT, the same microscope, just HT is high throughput. And next, we have our robust software suite that is integrated seamlessly with your microscope and easily allows us to interrogate your tissue microenvironment and perform advanced spatial phenotype mapping analysis. So these are our 3 here. So next we'll move on to multispectral imaging, also known as MSI. So if I say MSI, it's referring to multispectral imaging. So the multispectral imaging technique allows you to capture light in multiple fluorescence channels to visualize multiple biomarkers simultaneously. Conventional technologies only allow for imaging 4 biomarkers and DAPI using fluorophores with emission spectra that are spaced out and use narrow band pass emission filters to isolate emissions from each fluor. This strategy can capture a decent amount of emission for about 3 to 4 plex assays, but it becomes tricky once we go beyond the 4 plex. We'll do it. Okay, here we go. Attempting to image more than 4 biomarkers with conventional imaging technologies leads to an insurmountable excess of crosstalk. The problem here is that even though it's the use of narrow band filters, you still have bleed through where the emission from one fluor is picked up through the emission filter that's paired with another fluor. This is especially problematic with fluors that have broad emission spectra. For example, like DAPI, shown here in the diagram. DAPI signal bleeds through the FIT-C and TRIT-C channels. Autofluorescence, which is inherent to all of our samples, also becomes an issue because it can overpower signal from your target markers. When you go beyond, let's see if we'll do it. Okay. When you go beyond 4 markers, it gets massively messy between the channels, and it's impossible to use narrow band pass filter approach to isolate signal from one specific fluor. There's a lot of, as you can see here, there's a lot of crosstalk. You can see here between the 500 and 600 nanometer wavelengths. And so fortunately, our fusion can perform a process known as spectral unmixing to isolate each of these different signals and properly perform biomarker spatial analysis. Oh, no, forget anything. So there are three considerations to make in order to capture reliable data when performing multispectral imaging. The first we will go over is in order to capture the entire emission spectra, we need to map out the full shape of the dye response so that the system can distinguish between dyes with fully overlapping spectra within a single channel. So if we gather the data of each floor's entire emission spectra, we can much more accurately perform unmixing and quantification. There you go. And for, okay, so we've developed, so the way that we combat that is that we've developed a custom narrow multi-band pass filter cubes that are optimized to use with the opal fluorophores, as well as a proprietary autofluorescence filter cube. The instrument also uses an agile LED illuminator with 6 narrow emission spectra that are individually turned off and on to excite a single population of fluors corresponding to one of the excitation and emission bands in the multi-band filter cube. A combination of using the custom narrow multi-band patch filter cubes and the LED illuminators allow us to specifically map out each opal dye's full response. Once you gather that information across the entire wavelength of each opal, you can distinguish between dyes with spectral overlap within a single channel. The fusion performs our whole slide scan workflow, which is a one-step imaging process. For fusion, we take one multispectral whole slide scan. We then move into Phenochart, which is our viewing software for quick quality control of our image to view and perform pseudo unmixing and choose field of views to import into our Inform software analysis. We bring those fields of views into our Inform for unmixing and algorithm development for image analysis. Inform can perform cell segmentation, cell phenotyping, and spatial signatures. Okay, so the next consideration is once the entire emission spectra for each floor has been captured, we can then use that information to spectrally unmix signals in a sample multiplex image to overcome this crosstalk problem. Unmixing allows the system to distinguish between dyes with fully overlapping spectra within a single channel. We basically compare the measured spectra from our sample to a set of reference spectra to identify and separate signal for each floor. So this is a little harder. Okay. So here's a visualization of what spectral unmixing looks like and how it works. So if we consider this example, a 7-color 6-plex panel, the 6 markers are detected with 6 opal dyes plus DAPI as a nuclear stain. So if you can see here, we have all of our opals and each of their emission spectra, including the autofluorescence. So what unmixing will do is that, as we see here, we have each of these buckets. What unmixing will do is it will have each of the emission spectra into its correct bucket. So the Phenoimager is going to pick up all of the wavelengths, and our Inform is going to now correctly input each of those wavelengths into the correct bucket, so we don't have all of these signals in our DAPI signal. That's not what we want. We want to isolate DAPI, CD8 each of our markers. So that's exactly what our unmixing algorithm does. So it'll take it from our opal panel, image in our Phenoimager, and then moving to our Inform for unmixing. So how do we do that? So that's what we use our spectral library slides. So as alluded from the previous slide, spectral library slides are reference slides that the Inform software uses to determine how to unmix signals. So we have to tell the instrument, this is the spectra we are interested in, this is how it's measured, this is what we want to isolate. We train the Inform algorithm to recognize that wavelength through these library slides. What are library slides? They are slides that are stained with an abundant marker and one opal dye. So that way the instrument can capture the spectra of just one opal dye. So it does not have DAPI. So here we have some examples of what these spectral library slides look like. This here is the instructions on how to make those library sites, as well as how to acquire them on the actual instrument. So you can see here it says DAPI only. For tonsil, we recommend like CD20 for a tonsil, a very abundant marker. So these are all stained with CD20, just different opals. So here you have opal 480, 520, 570, and so on and so forth. And so this will allow us to image these on the Phenoimager, take them into Inform and train the software of this is a spectra of this one marker, and then we can perform unmixing later in Inform. Lastly, we need to account for the contribution of tissue-specific autofluorescence and autofluorescence from red blood cells or collagen fibers that are typically captured in the 480, 520 channels. And we want to remove that signal from our image when unmixing for improved signal to noise and more accurate phenotyping. So this slide illustrates the result of spectral unmixing. There's a huge difference in the raw image on the bottom left of the image. So here we have the raw image. Here we have our autofluorescence isolated, and this is our unmixed image. So you can just see visually how much more vivid the colors look because we're removing all of this from the background. They're also here in the graph, it results in an increase in signal to noise with a much cleaner image. In order to perform accurate autofluorescence removal during unmixing, you must also provide an autofluorescence slide, which is tissue specific for your study, which I'll go over the next slide. So here on the right-hand side, we see some data that supports the importance of removing autofluorescence from your sample. So you can see up to a 10-fold improvement of the signal to noise ratio. For example, we see here in 480, which is the channel where we typically detect the most autofluorescence. You see a signal to noise ratio increase from 88 to 1 to 999 to 1. In the bar graph below, we can also see you have 50% more accurate phenotyping after autofluorescence removal. There was an underestimation of cells for the number of CD8 cells, for example, which is missing almost half of our true positive macrophages. So you can see how important that is because we want to accurately phenotype our slides. So here is going to be the instructions on how to create the autofluorescence slide. So this autofluorescence slide will go through all the same steps as your multiplex tissue, except it won't have any dyes or any opals. So we want to do, we capture a lot of autofluorescence in our antigen retrieval and our heat steps. We gather a lot of autofluorescence in those steps. So what we want to do is we want to isolate that and we will train the algorithm to remove that from our tissues. So that's the purpose of this autofluorescence slide. And we recommend doing this on a tissue specific basis because each of our tissues emit different levels of autofluorescence. So if you're working with tonsil, you can create one for tonsil. You can use that for all of your tonsil samples. But we do recommend having different for kidney, brain, breast, whatever it is you're working with. Onto any questions on that? I know it's a big kind of theme to go over. Any questions on that before I move on to multiplexing? Or we can touch it to the end as well. We can do that. Okay.
Probably. So do the for the algorithm that separate
También me puede preguntar en español.
So se necesita, se hace cuando se setea el instrumento al principio o para cada experimento es necesario hacer, o para cada set de tinciones es necesario hacer eso cada vez. No sé si me explico la pregunta.
Para autofluorescence slide?
No, the autofluorescence one.
The library? The library, sí. So de los libraries no se necesita hacer cada vez. Eso nomás va a ser al principio. Okay. Porque lo que queremos hacer es que like the software measures that opal, so that's not going to vary with different tissue tissue types. So we have to do that one time.
With a mixture of antibodies of different fluorochromes.
See, so like they all of the so with the library slides, I'll put it back up so it's a little less confusing.
I mean, if you have a mix that has 5 different fluorochromes and another one that has 8.
Yes.
Do you need to do the like in cytometry the compensation for each?
Oh no. So if you have opals, say you have one assay that only has 4 opals, the next has 8. You can use the ones that are overlapping. You can use that for your 8-plex.
Okay.
Yeah, you don't have to redo.
Okay.
Yeah. It's the opal spectra will not vary because we know where those excitation peaks are.
Okay.
If you want to see 480 at 480, you can use an overlap in your different assays, depending on which ones you're using.
Thank you.
Claro. I have a question. Can you use only opal antibodies or mix opal and Alexa fluor, for example?
So you can use Alexa fluorophores. This instrument is optimized for opals, but the spectral range does overlap with Alexa fluorophores. So you can use the instrument for Alexa fluorophores. It's just not optimized for them. But if they're in the same wavelength, for example, you have 480 has the same wavelength, I forget which Alexa fluor. If they overlap, it'll still capture those Alexa fluorophores. So you can definitely still use Alexas. You can use a mix of both. And I have a conversion table I can show you as well, of which opals are in the same wavelengths as Alexas and different dyes.
Yo no entendí lo de la library.
Ujú.
Cuando mostraste el ejemplo de la tonsils,
Ujú.
eso
Sí.
significa que usaron un anticuerpo contra B220 con distintos colores para decirle al equipo cuál es el positivo. Entonces necesitamos tener todo ese rango de colores en algún antígeno que se exprese mucho.
So nomás sí, lo importante es que tiene un antibody que es abundante. Es porque decimos CD20, porque sí va a ser ahí en su
Pero
tonsil.
necesitamos comprar el CD20 en FITSI, en PE, en todo eso para hacer la library.
Sí. Ujú. So todos, como este ejemplo, todos estos slides tienen CD20. Más es CD20. Pero lo que es diferente es el opal.
No, eso está claro. Ella está preguntando otra cosa.
Yo no creo que hace
No
falta
te entiende, claro.
el mismo anticuerpo.
No
Lo
entiende. lo que está
importante es el mismo
Fluorocromo,
Fluorocromo.
pero un antígeno que se exprese mucho.
Claro, sí, bueno, B220, yo no creo que tenga que ser el mismo anticuerpo, tiene que ser el mismo fluorocromo.
Sí,
ahí por
Tiene anticuerpos primarios y después secundarios. Mismo B220, le ponen después el secundario y el opal que precipita va a ser de distintos colores. Pero te hace falta un solo. Si no vas a tener que comprar un anticuerpo con cada color como citometría, sino que usar el primario, el secundario. ¿Qué tal, Área?
Los secundarios.
Y o sea que lo importante y lo bueno que es que usa primario, es jugar. Y después le pones el color que quieras.
No, secundario es secundario no es distinto.
El segundo es el mismo, pero precipita después el color.
Opal, que es distinto.
O sea, vos necesitas todos los opal.
Con el B220 precipita un color.
También tengo otros slides que le va a ayudar. Perdón, Mariana. Sí. No, está bien. Ahorita le voy a explicar. Va a haber el multiplexing con opal. It'll make it a little clearer. Okay. So vamos a hablar qué es un opal. No, okay. Explicar un poquito más. Sí, okay. So the opal are fluorophores optimized for multispectral imaging, making multiplex results accessible to anyone who works with standard IHC. So the opals are tyramide signal amplification-based detection. So they have improved signal sensitivity up to 10 to 100 fold while maintaining resolution. They are stable because they are actually covalently bonded to our target epitope, and it allows us to multiplex with the same primary antibody species. Just provide some clarity. Okay, so aquí se ve un poquito más fácil de ver como how we stain with opals. So like I said, it's based on TSA, tyramide signal amplification. So just a quick overview of the opal chemistry. This schematic shows an example of the staining that is done automatically, or you can also do it manually. In this case, the triangles represent the antigens on the tissue sample. You would first come in with a primary antibody, and next, as you can notice as well, they're all the same species, so they don't have to be different species. You will come in with the primary antibody, and then you will then come in with a second antibody conjugated to a horseradish peroxidase, or HRP, and which catalyzes the conversion from the tyramide molecules to highly reactive free radicals, which causes the deposition of the opal fluorophore and immediately and very discreetly around the antigen. You would then come in with a heat-induced epitope retrieval step, which causes the dissociation of the primary and secondary body complex. So anything that is unbound is going to be washed away, and you are left with the opal fluorophore bound to your antigen. So as you can see, we have each of our primaries, we have the secondary come in with the fluorophore, we have them deposited, and then the heat comes and it'll wash it off. So you just repeat this step over and over and over again. Yep. Which can be done again manually or automatically on the stainer. And good to reiterate, it doesn't have to be different species. I know some staining, you have to layer the species. This you don't have to. It can all be the same species.
And how long does it take the incubation period?
Antibody incubation, I believe, is about 3 hours. Yeah. So here's just another schema. Oh. It's just another workflow, staining workflow that I was talking about earlier. So you would start with slide preparation, like deep paraffинization and tissue rehydration. You would then move to heat-induced epitope retrieval to unmask your target and give your antibodies access. Step three, after epitope retrieval, the slides are treated with a blocking agent to block potential non-specific primary antibody sites to decrease background and signal to noise. Our step 4 is going to be our incubation with our primary antibody. And then step 5, we're going to incubate our slides with our secondary antibody conjugated with HRP of the same species as the primary. And step 6, we have our TMA-based signal amplification, which is carried out by our opal dye deposition and the addition of peroxidates. The fluorophore, again, is covalently bonded to the tissue, and you will get amplified signals so you can detect low-expressing markers as well. And our step 7, the primary and the secondary antibodies are then stripped, and the process is repeated until each target is detected. This strategy allows us to use whichever primary antibodies work for us and to stick to one species, because the stripping step eliminates any cross-species reactivity.
Ariana, al orden práctico, cada estudio, vos tenés 3 horas de primario, puedes limpiarse, tenés que hacer otras 3 horas de primario.
No, los 3 horas va a ser para uno.
Media hora.
Media hora.
Solo media hora. ¿Puedes limpiar?
Sí.
Digamos, ¿cuántos ciclos en una día de trabajo? 2 días.
2 días.
7, 2 días. El total de...
Perdón, los 3 horas son para un ACE completa.
Ah, ok.
30 minutos para una. Sí, no, sí, para un pack completo, sí. De los 6 colores.
Sí, bueno, eso es eliminar los anticuerpos pegados y poder volver a marcar para la misma imagen. No, la podés superponer.
So aquí es un overview of opal assay development. So just a quick overview of how you're going to create your assays using opal. So first, we want to select a primary antibodies that are targets of interest, determine the best titer, and then run our DAB stains as reference for our tissue of interest. Next, we will decide on the suitable opal fluorophore to pair with each marker in our panel. So we have high expressors with our bright fluorophores, such as opal 480 and 520. And we would have our high expressors with dimmer fluorophores, such as opal 690 and opal 780. And we also want to keep co-localized markers spectrally distant. So if you have any markers that are co-localized, we want to make sure we're using opals that are spectrally distant on the ranges. And next, we will run monoplex slides with each of these pairings and evaluate against their DAB reference and look for similar staining patterns and intensity and fluorescence IHC. Our fourth is to determine marker position in its multiplex. So we will use serial sections and stain slides after the first, third, and sixth HIRE to evaluate the effect of different rounds of stripping on each antibody. So you want to have your position of your marker, but you want to see how well it does after each stripping step. So you would put it in the first, third, sixth, and see which one does the best. If you're seeing it does great at the first, or if it can do the sixth, leave it at the sixth position. The stripping steps will have an effect on the staining, so that's why you want to see where it's going to fit best in your panel. Next would be to prepare your spectral library slides and create those in Inform. And after that, we'd be able to run your multiplex and QC your imaging. So I have this guide as well. I shared it with some of the team, but if anyone wants to read that over, it's also on our website. We have the Opal Multiplex IHC development guide here. It's free to read. So if anyone ever has any questions, you can go through and read that. We also have additional Opal assay development resources. This is our website. So if you have any questions or anything like what is Opal again, or how do I multiplex, that's all going to be on our resources tab on our website. I think that's all I have. Eso es lo que tengo para ustedes. Si tienen más preguntas, también I have my email. Si quieren mandarme un email con preguntas, you can do that too.
Mariana, ¿el tejido en parafina o con frozen es la misma performance o
Va a ser diferente for fresh frozen and FFPE.
¿Y cuál es mejor frozen?
FFPE va a ser más, sí, puede ser los dos, pero preferible va a ser
Parafina me va mejor todas las cosas. Claro, por eso.
sí.
Y en el slide, digamos, en el portafolio, ponerle alguna de esas diferentes. No son diapositivas, los que entregamos. Los que tenemos.
Sí.
Sí, tenemos. Ok, positiva.
¿Cuál es el listado? ¿Qué cantidad de anticuerpos tienen ustedes marcados para la venta? ¿Qué espectro de marcadores cubren?
Tenemos demasiados marcos. En total.
En la página tienen el listado de y los precios.
Los precios no vamos a tener eso, pero tenemos nuestro reagent sales specialist que puede darle una lista completa de todo lo que tenemos y también los precios. Pero eso no vamos a tener nuestro.
¿Pueden comprar aquí en el país los anticuerpos o hay que hacerlo así para importarlo?
Yo creo que importarlo.
No tiene representación.
No.
Sí, como representante.
Pablo, representante.
I'm wondering whether we can use it with cells. You're able to fix them, then it will be.
Cells work too. We have a lot of TMAs, tissue microarrays with cells. You just get the core from the block and you're able to cut it onto a slide. I will warn with slides with if you create blocks using cells, I will warn that once you keep cutting, you'll get less and less. So just have multiple blocks.
But somehow you have, let's say, cell suspension, and you somehow fix in the slides, so you can.
Yeah. Yeah, we have a lot of people do that.
Perdón, Ariana, la pregunta de anticuerpos, ¿puedo usar todos los anticuerpos que tenés acá? O sea, no, lo que hace falta es el secundario y lo que precipita. Además, el secundario también se podría comprar y se pueden comprar los dos por separado. O sea que se podría usar todo lo que tenemos. El tema es
sí, pero no entiendo cómo podemos usar todo lo que tenemos cuando todo lo que tenemos lo tenemos marcado.
No, tiene que ser primario, tiene que ser
usar todo lo que tenemos. Cuando todo lo que tenemos lo tenemos marcado.
Comprarlo marcado. Compras un primario en cualquier compañía.
Tengo que volver a comprar todo de nuevo.
Si no tenés, claro, si no,
claro, puede ser cualquier marca. Claro,
bueno, entiendo, pero no hay. El sistema no está adaptado para lo que tenemos hoy disponible. La decisión que vayas a tomar implica una compra, o del primario, o del secundario, o de lo que vayas a decidir. Pero no lo que tenemos hoy. Lo que tenemos está todo marcado.
Hay que ver.
¿Podemos mostrar las equivalencias?
Claro, hay que ver eso.
Perdón.
Las equivalencias entre los cromos y los OPA.
Pero técnicamente está bueno, hay que ver, porque hay equivalencia.
Del
pero no lo va a precipitar, lo va a precipitar. Para que tengo que tener un secundario.
The chromogenic staining is just showing how that marker is staining. So it should be the same with opal. The staining should be comparable. So when you compare, when you stain with chromogenic, and you have their opal, it should be the same.
Can you show the list of the opals and the Alexa?
Yes, yes.
Si vos tenés tres Alexa,
Sí.
tienes que ver si no necesitas poner el opal.
Una cosa que funcione como el microscopio, se puede funcionar como cualquier microscopio que tenga una sustancia fluorescente. Y otra cosa es las bondades de los rangos que lo permiten
no sé
trabajar. Esto no te va a condicionar.
No sé si
Tienes que entrar. Vos pones una Alexa.
Sí,
Una Alexa, otra Alexa.
sí, aquí tengo la lista, perdón porque no estoy conectada por arriba, pero tienen todos nuestros scan bands que vienen siendo los opal. Después hay todos los compatible dyes, los Alexa floors, por ejemplo. Tenemos Opal 520, va a ser el mismo de Alexa Floor 488. So, si ustedes, if you stain with Alexa, también lo puedes seguir usando, nomás usa el Cube 570, Opal 570.
Pero sí o sí necesitas un secundario. El secundario que tiene que estar marcado.
Julio tiñó con sus primarios marcados con Alexa, levantamos y es comparable a lo que la gente que obtuvo en el confocal.
Entonces falta el precipitado.
No,
Porque
Con la
funciona
piel
como
con
un microscopio de fluorescencia.
Sí, sí, el multiplexing es lo que
Este
requiere, el multiplexing es lo que requiere el sistema de ellos con los DICE.
Claro,
Que además
para
es
que
doble
quede-
marca.
O sea, para que quede claro,
Eso
que
te
es la
aumenta
gracia.
la
O sea,
sensibilidad.
la multiplex es la gracia, si no, ¿para qué que volver a leer 4 colores en vez de en el otro? Se lo entiende mucho.
Si no usas el multiplexing, es que podés usar todo. Mientras puedas cambiar, por ejemplo, con anticuerpos que ya tenés y entrar en los filtros que estaban teniendo, que son 6, por ahí que tengas 4 o 5, después podés usar el info, ¿no? El info te va a contar todas las células, te va a hacer la talla que por ahí no tenés en todos los microscopios para hacerlo, te debe un poquito más, te daría armar. Ese es el otro beneficio.
Facultad de Ciencias Químicas.